Hello everyone, can you hear me? Okay. So, hello everyone and welcome to the talk on Introduction to the Basics of Optimization. So, interrupt me with questions anytime in the middle of the talk. I hope you ask lots of questions and make this an interactive session. Okay. So, we'll start with the quote, which I'll read it out loud to you in a strange voice so that you make it clear. Since the fabric of the universe is most perfect and the work of a most wise creator. So, as Wikipedians here, we feel that there must be a citation needed here, but we'll continue. Nothing at all takes place in the universe in which some rule of maximum or minimum does not appear. So, if the double negative confuses you here, it means that everything involves optimization. That's kind of the statement here. So, this statement was given by this fashionable gentleman here. So, can anyone guess who this is? Yes, indeed, it's Leonhard Euler. He is one of the most influential mathematicians in history and the most prolific one. I will try to convince you this statement is true to a certain extent. I'll try to show you that optimization is pervasive. It's in every part of the universe. So, by giving some examples. So, first consider a simple example where you just say you throw a ball up and then you catch it. So, what you do know is the ball was at your hands at say at height 0 at time instant 1 and it was back in your hands at time instant 2. But what happened between those two time instants? What was the height of the ball between those two time instants? Obviously you know the answer to it because you apply all the Newton's laws of gravitation and stuff. But assume for now you don't know Newton's laws. Assume for now you don't know Newton's laws. The only thing you do know now right now is the law of conservation of energy. That's the only thing you know. In this case, can you say anything about what happens between time instants 1 and 2? Can you? Can answer. Okay. The answer is you really can't. I mean, this is a valid trajectory. Any of these are valid trajectories. I mean, if the law of conservation of energy is the only thing you had, there are lots of valid paths. Every one of them is valid. But what might be surprising for you to know is you can find the correct path, the true path from an optimization out of these paths. So this is known as the path of least action. And where you define action at a point to be the difference between the kinetic and potential energy, and action at a path to be the integration of action at different points over the path. This was called known as the principle of least action, and it was proposed by Pierre-Louis Moreau de Maupassant. I'm not too sure if that's the right pronunciation. If anyone of you knows French, please feel free to correct me. So here you can use this principle to get the trajectory, the path of the ball, which seems like a pretty simple problem, but this can be used to pretty much derive almost all of classical physics. So this is a very powerful principle indeed. So it's a very powerful principle, and the core of the thing is optimization. That is, you're doing optimization over paths. That is, you're choosing the path of least action. Okay, so it says the universe does optimization. Okay, I'll try to give you more examples. Consider an example from chemistry. I'll tell you that the molecule structures themselves are optimizations. For example, say consider a simple water molecule, which is H2O. If you don't remember, it consists of two OH bonds. So the structure of the molecule is defined by two variables. That is basically the length of the OH bond, say denoted by R, and the angle between the two OH bonds, denoted by theta. Okay, so every such R and theta leads to some energy of the configuration. Sorry. For example, for different values of R and different values of theta, the configuration has some energy. As many of you might know, the least energy configuration is the most stable one, and that is indeed the structure of the molecule. So the structure of any molecule actually is a result of an optimization problem. So whenever you're looking at nothing and you think you're seeing just air, you're seeing billions of molecules, every single one of them a solution to an optimization problem. Okay, so you cannot escape optimization. So that's kind of the theme here. Okay, so this is not the only. There are many other examples. For example, Pierre Fermat's principle of least time states that the path taken between 2 points by a ray of light is the path that can be traversed in the least time. So this is a very powerful principle and can be used to derive almost all of optics. For example, it can be used to derive the Snell's law for refraction angles that you would have studied in school. So in particular that, so can be pretty much used to derive all of optics. It's again a very powerful principle, the core of it, optimization. Once again, for an example in thermodynamics, Gibbs states that for all thermodynamic processes between the same initial and final state, the delivery of work is a maximum for a reversible process. I absolutely don't know what this means. I just wanted to show that optimization comes also in thermodynamics. So if any of you know what this statement better means, well, you can feel free to tell me. So, okay. Another example is Occam's principle that says that among competing hypotheses, the hypothesis with the fewest assumptions should be selected. This is a very, very interesting statement, and in fact, I'll try to illustrate to you with an example. Say, assume you are here listening to me talk, and suddenly you fall asleep, which I assure you is quite normal. And then you wake up, if you fall asleep for 5 minutes, and then you wake up, and you see me, I'm still here talking, and your friends are still here nodding their heads. So what do you assume happened during those 5 minutes? What would you assume? Nothing. Yes, you would assume that I was continuing to drone on and you were continuing to listen here. Why did you assume that? Why did you not assume that aliens came from Mars, kidnapped every one of you except you, did some pretty painful experiments on us, and returned us back in 5 minutes? That's just as valid an explanation of what happened with your data as the explanation that nothing happened, right? Why did you not assume this, the second explanation? Yes. Pardon? Yes. True. So that's exactly the Occam's principle. Whenever you make a statement, you are actually using Occam's principle every single time. You may not be aware of it, but the very fact that you assume that everyone remained here, you actually applied Occam's principle. So this is a pretty basic principle and is there and is pervasive. And pretty much in every statement you make, you are actually using Occam's principle. Okay? So I think I've tried to convince you that optimization is pervasive. It's everywhere. It is in the fabric of the universe itself. And if at all you want to understand the universe better, that is, do science, you must understand optimization. If this is not reason enough, I'll give you more. That is, optimization is not pervasive only just in science and the universe. It is also pervasive in everyday life and engineering. For example, consider the problem that you solved today morning. You are in your hotel room and you wanted to come to the summer school for the department for summer school. So what did you do? I mean, at least you tried to solve, or at least you asked Google to solve this problem for you, which is, okay, I'm here and what is the path to here? So what did Google or you do? It really calculated all the routes and found the shortest path. So this is again an optimization problem. Clearly there is a shortest here. So this is an optimization problem. You just solved it today morning, at least. Some of you, okay. So this is, as computer scientists at least, I don't really need to give the importance of optimization to you because most of computer science is optimization, really. But these kind of problems are like somewhat more special in the sense that they are not just optimization. The number of candidate solutions are only finite. For example, here, the number of paths from your hotel room to the department would have been like maybe 8 or 9. There are only that many number of paths. Of course, in a larger graph, it may be much, much higher. But the key thing to notice, the number of possible solutions is only finite. So these kind of problems are known as discrete optimization problems. And these are the kind of problems you would have encountered in computer science throughout your course or something. For example, the shortest path, or the maximum cut, where the possible solutions are subsets of vertices in a graph, or the minimum vertex cover, where once again the solutions are subsets of vertex in graphs, or the maximum independent set, or the maximum matching, or the minimum cut. So I can keep on going. I mean, pretty much I need to do nothing. I just need to go to compendium of optimization problem, NP optimization problems, and I can get like maximum, minimum pretty much in every single one of them. So optimization is not alien to you. I mean, you've been doing optimization throughout your life, at least studying optimization. But discrete optimization is slight bit more intricate in the sense that even though you could do a brute force solution, which completes in finite time, you can do it, but it is really not computationally feasible. For example, if you wanted to compute the maximum cut, even if you had a graph of 40 nodes, you'll probably have to wait till the end of the universe to actually compute a brute force solution with reasonable computers. But of course, there are algorithms. For example, the Dijkstra algorithm that you probably used in the morning today, it does solve the shortest path problem, but it cannot be used to solve any of these other problems. It can be used to solve the shortest path problem and only the shortest path problem. So the algorithms for these kind of problems are kind of pretty unique in the sense that you have to use a different algorithm for different problems. There is no unifying framework of sorts here. Of course, there are a few, but it's very distinct for each of these problems. So, but what we will focus on is actually a continuous optimization problem. For example, the line fitting problem, which you did in your school when you took a resistance wire and varied the voltage and measured the current and to calculate the resistance. You would have definitely done this. Okay, vary the voltage, find the current, and find the resistance. So each resistance there corresponds to a line. And every possible value of resistance fits your data to a certain extent. Call that the measure of fitness. What you want to find is the resistance that fits the data best. That is, you want to find the resistance value that gives the best value of fit. So that is again an optimization problem. But here, however, the resistance values are not finite. You don't have like 1 value or 10 value or even 100 values. You have infinite possible values. It's continuous optimization. This is what I call continuous optimization problems. So these kind of problems, in some ways, they are actually more complicated because at least in discrete optimization problems, if there's only a finite number of solutions, even though it might be computationally hard, it is at least possible. But these kind of problems, it is possible that you can never even get to the answer because of infinite solutions. And that is indeed true. Continuous optimization problems in general are more difficult than discrete optimization problems. But however, in most practical continuous optimization problems, there is some kind of structure to these problems which enable you to solve these problems efficiently. And these kind of problems are also all pervasive. For example, these are the norm in machine learning or statistics. And in fact, the previous line fitting problem falls squarely in this category. It falls under machine learning or statistics. For example, say if you are a circuit designer, your optimization variables now are the transistor widths or something. And your optimization objective would probably be to minimize the delay or maximize the gain or minimize the noise or something like that. So once again, there your optimization is a continuous optimization problem. Or you could be a civil engineer, which I know you're not, but you might want to construct suspension bridges where you would want to minimize the number of supports, but at the same time, still ensure that people don't fall off bridges or the bridges don't fall down. Or you could be an operations researcher, which is really nothing but continuous optimization. And somewhat more interestingly, many of the discrete optimization problems can be relaxed to form continuous optimization problems. And that is indeed what you will actually do in most cases. So I think I've convinced you why continuous optimization is interesting and what continuous optimization is. So if you have any questions, you can ask me. Okay, so for example, almost all of these problems, for example, the max cut problem, you can relax it to form a linear programming problem, or you can relax it to form what is known as a semi-definite programming problem. So I'm not really giving you, I'm only giving you terminology so that you can search later, but the best maximum, as you might know, the max cut problem is NP hard, so you can't really hope to solve it efficiently, but the best approximation ratio known is actually by relaxing this maximum cut problem to a semi-definite programming problem and solving it. So that's in fact how most approximation algorithms work. What they do is they take a discrete optimization problem, they relax it to a continuous optimization problem and solve it, and then derive a discrete solution out of it. In that case, you can't, because as most of these are NP hard problems and you can't really guarantee exactness, but you can actually guarantee approximation ratios, and that is how most approximation algorithms work. Okay, so I'll now illustrate continuous optimization with like a very, very simple toy problem. So it might be kind of funny though. So assume now there is a hungry cow at position 2,2, okay, and you are a very cautious fellow and you tie it to a rope of 1 unit long. So that means that the cow is restricted to remain in this circle. As if that were not enough, you are also a cruel master. So you keep grass outside the circle. And as if that were not enough, you still do something more. You have an electric fence passing through this point. So please don't let PETA people know that you're doing this. They might prosecute you. So the question you can ask is, how close can the cow get to the grass? I mean, it cannot reach it. Of course, the constraints are being that it must not strangle itself or it must not electrocute itself. So that means that it cannot really go beyond this line or go beyond this circle. So you can ask the question, how close can the cow get to the fodder? Okay, so this is a toy problem, but still, this is a valid question to ask. Now, I'll frame this problem as an optimization problem. So what do we want to find here? We want to find the position of the cow. So let's call it x, y. Okay. So what do we want the solution to satisfy? We want the solution to be as close as possible to the grass. So the grass is at 4, 3. So the distance of x, y to the grass is simply x minus 4 squared plus y minus 3 squared. So it's the distance squared, but still it's the same thing. Okay. So we want the solution to minimize this. But under what constraints do we have? I mean, under the non-strangulation and the non-electrification constraints. The rope constraint ensures that your x, y must stay within a radius of 1 from 2, 2. That is, x minus 2 squared plus y minus 2 squared must be less than or equal to 1. The fence constraint ensures that you stay to the left of this line. So that means that your x must be less than or equal to 2.5. So I'm sorry here that this is the x coordinate, this is the y coordinate. I should have probably had a label here, but it's fine. Okay. So the fence constraint says that x is less than or equal to 2.5. Now we are ready to frame the optimization problem now. So our variables are x, y, which indicates the position of the cow. Our objective is to minimize x minus 4 squared plus y minus 3 squared, which is the distance from grass. Okay. And the constraints are x minus 2 squared plus y minus 2 squared is less than or equal to 1, and x is less than or equal to 2.5. Okay. So this is how any optimization problem looks like. It says minimize or maximize an objective, which is a function of variables, subject to constraints, which are also constraints on the variables. Okay. So this is how a generic optimization problem looks like. But how are we going to solve this? I mean, we have no frame. So every optimization problem, I mean, as engineers, you will have to face two phases. One is you will not really be given optimization problems. You will be given, for example, this cow problem. So in this case, you have to first frame it as an optimization problem and then solve it. So there are two real steps here. Okay, now we have framed the problem. This was not so difficult. But how are we going to solve this? Assume for now you are a more free person where you let the cow free. That's an unconstrained case where there is neither a rope nor the fence. So in this case, your objective is to just minimize x minus 4 squared plus y minus 3 squared. Okay, that's one thing. So yes, so in this case, you know the answer. It's really 4, 3, the answer. But forget now that. But the other way is actually to set the partial derivatives with respect to x and with respect to y to 0, or in other words, set the gradient to 0 and solve it. That's a very powerful method, and of course you need to check some second order conditions, but still setting the gradient to 0 and solving it is a powerful method, and if you can do it, you should do it. In this case, you really can do it, so you should do it. But there are a lot of cases where you can't either take the derivative, or even if you can take the derivative, you can't really solve the equation. That is, gradient equal to 0 requires you to solve an equation. You might not be able to find roots to that equation. So there are cases where you can't do that. So in that case, what do you do? Okay. So in that case, what we do is, in general, a general framework is to use an iterative solution. That is, you start with the candidate solution, and then you keep on changing the candidate solution so that hopefully the candidate solution keeps on improving. For example, the cow could start at 2, 2. Okay. So in which case the objective is 5. Or then the cow could move to some other place. Cow could move to 1, 4, in which case the objective is 10. Or then the cow could move to 5, 2, in which case, okay, I think the lines are wrong here. It's 4, 2, and in which case the objective is 1. So you could like do a search. This is kind of like almost like brute force search. You could do it. This is one way to do things. But this is not really using the this is almost like solving it as a discrete optimization problem, right? I mean, the main reason why we are focusing on continuous optimization as opposed to discrete optimization is it has some kind of structure. So if you are just evaluating functions at different points and doing it, there is really no different from a discrete optimization problem. Assume the cow is real, what would that cow do? I mean, it would not really, assume that cow is not capable of teleportation, so it cannot teleport. So it can only move. So at every point at the solution, it has to have a direction to move, right? So the question now then becomes, needs a good direction to move from the current point. Most of optimization is actually finding out what is a good direction, right? I mean, you are at some 2,2, what is a good direction to move in? So that's a question you ask very, very often in optimization. Okay. So now the question is clear. I will make a small detour to explain what this answer this question. Okay. So first consider functions of one variable, f of x, and you can do a Taylor series expansion, which is f of x plus epsilon d is f of x plus epsilon d f dash of x and so on. I hope you are familiar with the Taylor series, but even now, even if you are not, assume that this is the Taylor series expansion. And for small enough epsilon, you can ignore the second order terms. The second order terms vanish. So the only thing of concern is the first order term. So now d is the direction. So what do we want now? We want our f of x plus epsilon d to be smaller than f of x. Now we are already at x. We want to find a direction d such that if we move along that direction, we reduce our objective, right? That's what we want to do. So we want our f of x plus epsilon d to be small, which in other words, f of x plus epsilon d minus f of x is really nothing but epsilon d f dash of x, right? So now the question becomes, what should be the value of d such that epsilon d f dash of x is as small as possible? And in fact, it should be negative. As long as it's negative, you are fine because you are in a direction of descent. So in here, it's really clear, right? You just choose d to have the opposite sign as f dash of x. If that's the case, then your d f dash of x is negative and you are fine. So that is indeed the case here. In one dimension, there are only two real directions, so it's not really too difficult, but still, it says that the negative derivative is the direction of maximum descent. So this is, for one dimension, is not very useful or very illuminating, but this is a statement which is still sensible. This statement becomes much more informative in higher dimensions. If you have a function of more than one variable, now you have, say, you have f of x plus epsilon d. Again, you can write a Taylor series expansion. But here now, instead of a derivative, you have the gradients. That is, f of x equals f of x plus epsilon d equals f of x plus epsilon d transpose grad f of x plus second order terms and so on. Once again, for small enough epsilon, you can ignore the second order terms. They are negligible. But what is grad f of x? This is the gradient I mentioned earlier. So this is the generalization of derivative to more than functions of several variables. And d transpose grad f of x simply means for two vectors a and b, a transpose b is simply the dot product of these two vectors. Okay, so it's okay. But here, once again, for small enough epsilon, you can ignore the second order terms, and f of x plus epsilon d just turns out to be f of x plus epsilon d transpose grad f of x. Once again, you can ask the question, you want to find a d such that f of x plus epsilon d is less than f of x. In other words, any direction d such that d transpose grad f of x is less than 0 is a descent direction. That is, if you go along that direction, your function value decreases. And in fact, choosing d equal to minus grad f of x in particular gives the direction of steepest descent. This is what I meant in the previous statement. And I said that the direction of negative gradient is the direction of steepest descent. So this, for example, say if you had a function of two variables, this was your grad f of x. The red line corresponds to directions where d transpose grad f of x equal to 0. In other words, these are neither descent nor ascent directions. Directions on this side of the line correspond to descent directions. That is, set of directions where d transpose grad f of x is less than 0. Directions on this side of the line, that is the same side as the gradient, correspond to ascent directions, or d transpose grad f of x is greater than 0. Okay. So that what this means is any direction that is on the opposite side of the gradient are good directions. Recall now what our question earlier was to find a good direction, and descent directions are really good directions. That's the kind of statement I hope to try to make here. Okay. So we'll illustrate with a simpler example than that, a one-dimensional function, that is y equals x squared plus 2. So it's a simple function. Okay, so you are at some point, say 0.8. You know the solution here is 0, obviously, so you know the solution. So in this case, you want the direction to be to the right. And if your x was minus 0.5 instead, okay, I think I'm confusing things. So if your direction was minus 0.5, if your current position was minus 0.5 instead, your direction is to the right. Okay, so I always get confused with the right left. Okay, so in general, if your current x is greater than 0, then your direction is to the left, and if your current x is less than 0, then your direction that's the right direction to go, right? If you have a new how do you update from a new x to a current x? You just add your d. Okay, so really, how can you choose d? I mean, I've given enough hints now, so you just choose the negative of the derivative. The derivative of current x is simply 2 times current x, so choosing the negative of the derivative does the trick, really. I'll illustrate how it works now. So for example, your current x is 0.5. The negative derivative, d, is basically minus 2 into 0.5, which is minus 1. So if now your new x becomes just current x plus d, or in other words 0.5 minus 1, just minus 0.5. So now you iterate from 0.5 to minus 0.5. Okay, so now you would do the same thing at minus 0.5. The negative derivative at d is minus 2 into minus 0.5, which is 1, and you update it and you get back to 0.5. So now you see what happens, right? I mean, the reason is obvious, right? The reason is that all of these first order conditions hold for small enough epsilon. Only for small enough epsilon can you ignore the second order terms. Here the epsilon is just not small enough. That's the real reason. So you must choose a right step size. You must not add directly the d, but rather reduce it by a certain factor. Okay, so can you think of a solution to modify a step size for this to work? What? Yes, yes, that would work. For a small enough constant, it will work. So now there you can see a trade-off. If you have large values of step size, this might happen. You might end up oscillating, or it might even get even worse. But for very small values of epsilon, once again you are in trouble, right? Because you will not move much at all. I mean, the new x will be almost the same as current x. So there is a trade-off here. You must choose your epsilon large enough to ensure that there is some progress. At the same time, you must choose your epsilon small enough to ensure that this kind of oscillation does not occur. One very popular method to kind of solve this is to actually start with a large step size. But as you proceed further, you actually keep on reducing the step size. This is a very popular approach, but it's not really needed. If you choose, as I said, if you choose a small enough step size, it will work. But in a lot of cases, you don't know how small is small enough. For some problems, 0.1 is small. For some problems, only 0.01 is small. So in such cases, this way of choosing the step size, decreasing step size with the iteration is a very powerful method. Okay, so I'll just summarize this algorithm, which is the famous gradient descent algorithm. So this is the algorithm I mentioned when I said there is some kind of framework in continuous optimization you can use it to solve, unlike the discrete optimization where there is no generic algorithm. The generic algorithm I meant for continuous optimization is the gradient descent. So the algorithm is very simple. You just start at any position, current position, you find the gradient, and you update your current position simply as current equal to current minus step size into gradient, and you keep on doing this. So this is the famous gradient descent algorithm, and this is kind of ubiquitous. You pretty much do it almost everywhere. For example, if you are electronics engineers, you would probably have some filter learning or something like that, and you would see that even though it's not explicitly mentioned, the gradient descent makes an appearance. For example, if you had gone through a neural networks course, there would be something like a Hebb learning rule or something, and that is really nothing but gradient descent. A lot of these rules and a lot of these rules in cognitive neuroscience and stuff like that, they actually turn out to be some versions of gradient descent. So gradient descent is a very powerful and very ubiquitous method, and it's very simple as well. So just see, so there's a negative gradient at 2, 2 is really 4, 2, and it points towards the grass. So it's a happy direction for the cow. At the same time, if the curve did not start at 2, 2, but rather started at some other point, say 1, 5, still the negative gradient points towards the grass. It's still a happy direction for the curve. So, like, just summarize the gradient descent method. So it's like it is a very simple method, and it is very easy to implement, and it is very powerful. In fact, you can show that if you choose the step size properly, it always converges. It provably converges to a local minimum. So, do you know what a local minimum is? I mean, it's something like this. Should probably have to add a figure. But so, this is the global minimum of the function. This is x, and this is f. This is the global minimum. But this point, even though there is a better value than that, this, locally it is fine. So it's a local minimum. So what you can guarantee with the gradient descent is only convergence to a local minimum. So can anyone tell why the gradient descent does not converge to a global minimum? Yes. Yes. So yeah, once it gets to a local minimum, the gradient there is 0 and there is no update. I mean, that's how it is. So it does not converge to a global minimum. Okay. So this is for gradient descent. So you can just as well do something else. I mean, this was for minimization, but if your objective was maximization instead, how would you change the algorithm? Yes. Instead of negative gradient, you just choose a positive gradient. So that would give you a local maximum. So pretty much the same analysis anywhere. Okay. So recall that the negative gradient is the direction of steepest descent, but there are a whole host of different directions. They are all valid descent directions. In fact, you can pick any of them, and there are more advanced methods which, instead of picking the gradient directly, picks a descent direction, some sophisticated manner. So there are a whole host of other methods which pick a direction which is not exactly the gradient, but it is still a descent direction. For example, there are other methods like the conjugate gradient method, the quasi-Newton method, the Newton method, and so on. Okay, I think I answered the question already, but the question is, can you come up with a method that picks a different direction than just the negative gradient? Well, okay, I answered the question already. So it's the Newton method, yes. So the Newton method, what it does is it takes a matrix, and instead of just using the gradient itself, it operates the gradient with the matrix, and that ensures that it still is a descent direction and uses it. So I'll not really go into the details of it, but that's what the Newton method does, and it's a better method than that. So I'll try to show a demo of gradient descent that a friend of mine wrote. So it's all credit for the demo goes to Saneem. So okay, so it optimizes a fixed. Can you see what's happening here? So here I give the step size of it. So step size, say I pick 0.2, for example. Okay, so this is the function that's being optimized. Can you see the function? Can you see the function? So I'll just illustrate how the function looks like. This is the function. So this is your function to optimize, and this is the contour plot. Okay. So the contour. Pardon? Okay. So now I will give the initial point, and based on that you can see how the gradient descent algorithm works. For example, I pick this point to be the initial point, the point at the corner there. So I pick that here, and this is the solution. You can see that the solution, it converges towards the solution. So here there is only one minima, so it's fine. So you can see how for a small step size it converges fine. Okay. Okay. Now I'll try increasing the step size and do the same thing. Okay. I'll give a step size of 0.5 now instead. See what happens. The same function. So I'll choose the same value maybe. Okay. Now see what happens. Okay. Now you can see what happens, right? I mean, it started somewhere and it began to oscillate. And it doesn't really, it passes through the minimum. So here, as long as you had chosen any step size that is smaller than 0.5, it would have worked. So 0.5 would oscillate, and anything more than 0.5, it would diverge. It would go beyond, and I'll probably show that as well. For example, if we choose 0.6 instead, it actually every time it goes beyond and the width of it keeps getting bigger and bigger. So you should be very careful with the steps. The step size is a very important parameter to choose. So you should, that's one thing you should learn with gradient descent. Okay. Okay. So that was for unconstrained optimization. We still did not consider the very strict owner who puts ropes and fences. So that becomes a constrained optimization. So how would you solve that problem? In such case, a simple variant of gradient descent known as projected gradient descent actually gives results. I will not really give the details of this variant. It's simple to describe, but actually somewhat difficult to actually execute computationally. So that's why this is not really always a good method to use, but at least conceptually this is a good method to use. There are more advanced methods and they require more powerful machinery. I mean, the first step is for constraint problems you set the statement like set grad f of x to 0 and solve, right? You must at least get to that level of understanding for constraint problems as well. So to get that level of understanding we need more powerful machinery, and that's what I will kind of try to emphasize in this. So in constraint optimization we will consider a simple case where you objective is to minimize f of x subject to g of x less than or equal to 0. These are your constraints. Okay. So given any point x, now we can define two types of direction. That is a descent direction, which we saw earlier was simply the set of directions that are opposite to the gradient. And you can also define a feasible direction, which is the set of points you can move and still satisfy this constraint. So assume someone gave you a solution and says this problem and gives you a solution x star and says this is the solution to x star. What should we expect out of this solution x star? Firstly, it must be feasible. It must have g of x star must be less than or equal to 0. Otherwise, this does not even satisfy it. Secondly, there must not be a descent direction that is also feasible. If that is the case, if there is a direction which is both a descent direction and a feasible direction, you can just move along that direction and remain feasible. That is, still satisfy the constraint and still reduce the function. So that is not the optimal problem. So this is what characterizes the solution. It means that it must both be feasible and there must not be any intersection between the descent direction and feasible directions. So that actually pretty much characterizes the problem. So recall how would it look like? For example, now again the problem is the same. There must not be a descent direction that is also feasible. So this solution was some x star. Now there are two possible cases. One is one is this x star is such that g of x star is actually strictly less than 0. Or g of x star is on the boundary and g of x is equal to 0. There are two possible cases. In the case that g of x, it's official, it's gone. In the case that g of x is actually less than 0, we can see that this feasible direction, I mean, because g of x is less than 0, you can move in a small radius around the point x star and still remain feasible. So that any direction you move is actually a feasible direction. So the set of feasible directions is actually the full set. Any direction is feasible. So the only way you can satisfy this constraint, that is, there must not be a descent direction that is also feasible. The only way you can satisfy that condition is no direction is a descent direction. That's the only way you can satisfy this condition, because every direction is a feasible direction. Only way you can satisfy this condition is to have no direction to be a descent direction. So when can you have no directions to be a descent direction? When does that happen? Yes, when your grad f of x is already 0. Recall, your descent directions are the set of directions where d transpose grad f of x is less than 0. So if your grad f of x is already 0, it's not possible. So that means that this reduces to an unconstrained problem. So you just, in cases where the solution x star is actually strictly at g of x less than 0, in that case, it's pretty much an unconstrained problem and there is nothing really interesting going on here. I mean, you can just as well solve the unconstrained problem and get the solution. The interesting case is when g of x star is actually equal to 0. In that case, not all directions are feasible directions. So there is some kind of structure that is possible. For example, say this was your grad f of x star. So what are your feasible directions? The the shaded red part becomes your feasible directions. So here, now what, sorry, I think I made a mistake. The red directions are the descent directions. Okay, so now recall now g of x star was set to be 0 now. Now what are the feasible directions? You can clearly see that feasible directions are really nothing but the descent directions for g now. Right? I mean, your g of x star is already 0. The only way you can have a direction to go into and still g of x star to be less than 0 is if you have the direction to be a descent direction for g now. So that makes life a little bit easier for us. So now you can have your g to be grad g of x star is this. Then the descent direction for grad g of g, or in other words the feasible directions now, will be given by the green things. So here you can see there is a clear intersection between the set of descent directions and the set of feasible directions. Clearly there is an intersection. So when can there be no intersection? There is really only one possibility. That is if your grad f of x star and grad g of x star point in opposite directions. If that's the case, then there is no intersection between the feasible direction and the descent direction. Or in other words, there must exist some positive lambda such that your grad f of x star is minus lambda times grad g of x star. Okay. So for now we'll assume that this lambda is a magical number that is given to you by somehow by the supreme being. If this, what does this lambda give you actually? So what does lambda gives you is actually it turns a constrained optimization problem into an unconstrained optimization problem. So this in particular also takes care of the case that your g of x star is actually strictly less than 0. If your g of x star is strictly less than 0, your lambda becomes 0. So in that case also you're fine. So your grad f of x star to be equal to 0. So there is no need to handle it separately. You can handle it via the lambda itself. But still, I'm not told you how you get this lambda. I will not tell you. So assume for now it's the lambda is a magical number given to you by someone. So now you have a constrained optimization problem, that is minimize f of x subject to g of x less than or equal to 0, something like that. You want to satisfy, now someone gives you lambda also. So you want to satisfy this condition, that is grad f of x star equals to minus lambda g of x, grad g of x star. Immediately it means that instead of solving this problem, you could just as well solve this unconstrained optimization problem, which is you minimize, instead of minimizing f of x subject to g of x less than or equal to 0, you minimize f of x plus lambda g of x over x. This is an unconstrained problem. So if you take the gradient and set it to 0, you will get back the condition. Right? So this is the first step. I mean, now you have reached a level of understanding where you can say, well, for unconstrained problems, you are setting grad f of x to 0 and solving it will solve the problem. Here, now there is another additional step, that is you need to find the lambda. But if you can find that lambda, now you can have the same understanding as an unconstrained problem. So I will not really tell you how to get that lambda, so forgive me for that. So this lambda is called the Lagrange multiplier, and that is the main character of this part of the story. So it has roots in physics and stuff. I mean, that's how most of mathematicians in the 18th century derived stuff, like they had links to physics. Okay. So I will try to show a small demo for this as well. It will not be as illustrative as that, but still it will be. So the problem was minimize f of x subject to g of x less than or equal to 0. G of x was simply a circle constraint. Okay. So at every point I give you the blue line and the red line gives you, the blue line gives you grad g of x and the red line gives you grad f of x. So I'll show how it looks for different points in the curve. For example, at these points you can see that they are almost in the same direction. These are not what you want. As I mentioned earlier, you want your grad f of x and grad g of x to be in opposite directions. Of course, I'm not giving you the lambda, but take it from me that lambda is not 0. So really, you can see that as you go along, as you move there, it seems that the two lines get opposite as you move up. That's how it seems, right? So here it seems to punch to the right, and here it goes to the left. So it means that, okay, this seems to be. Once again, the solution should be at the boundary, because if it's not at the boundary, then it makes no sense, right? So you would expect something like this to be the solution. This seems to be fine. I mean, it's almost at opposite directions and it's at the boundary. So let's see what the function actually is. Okay, these are the contours of the function. You can see that there's a point. Okay. This is a 0.5 contour. This is a 1 contour, and the point that I chose is pretty close to the. You can see that this is pretty close to the optimization that I want. So I'm not giving you the lambda, but still, this is kind of the intuition that we want you to gather. It is, we want your constraint gradient and your function gradient to be at opposite directions for a non-zero lambda. If your lambda was 0, then the constraint you can just as well ignore it. Okay. Okay, that completes the main part of the talk. Okay. If you have any questions, you can ask me now, because this is something which I prepared in case that we have like too much time left. But I think 10 minutes is a reasonable, good enough time. So if you have any questions, you can ask me. Okay, then maybe I'll just give a teaser then. So, as I said earlier, general continuous optimization problems, solving them to global optimality is actually not easy. Local optimality is easier. I mean, you can use gradient descent and get something. But global optimality is very hard. But there are a class of problems where local optima are actually global optima. They are exactly what is known as convex optimization problems. It's a very general class of problems, and it includes linear programming, quadratic programming, semi-definite programming, and so on and so forth. The reason why I'm telling you this is, as I mentioned earlier, there are two parts to an optimization problem. I mean, to learning optimization. That is, framing your problem as an optimization problem, and secondly, solving it. So they are very intricately connected things. I mean, you must ensure that you frame your problem as a solvable problem. I mean, you can frame your. I mean, if you just want to frame your problem as an optimization problem, it is probably easy to do. But not all optimization problems can be solved easily. There are only, for example, convex optimization problems can be solved easily. So mostly the name of the game in engineering is to frame your problem as a convex optimization problem. So that's going to be mostly if you are an operations researcher or if you are a design engineer, mostly that's going to be what you'll be doing. There will probably be generalized routines for solving convex optimization. You will most likely not touch that. I mean, of course, for more specialized structures, you will have to write those algorithms as well. But most of your work will probably be to frame your problem as a convex optimization problem. So that's how most of your work will most probably be. So I'll give you an example which how complicated problems can actually become convex optimization problems. For example, assume you are given m points, x1, x2, xm, n-dimensional points. Okay. So now your objective is to find the smallest ellipsoid covering them. For example, say what happened? Okay, cool. So if you had, say, these many points. By the way, can you see the board? It was black. I think yes. You could have, say, points like this in R2, so there are only 2-dimensional points. Your objective is to find the smallest ellipsoid covering this. So here it's like simply this. When I say smallest in volume, so of course this is not an ellipsoid even, but assume this is an ellipsoid. So your objective is, this is a pretty important problem in a lot of cases. I mean, this occurs as a very good subroutine. So you can define an ellipsoid to be a set which satisfies these kind of constraints. So in case you don't get it, you can just imagine your this instead of a matrix A, you can just imagine as a constant C. In which case you can see that the set of vectors that CV plus B is norm less than equal to 1 is simply a sphere with center minus B by C and radius 1 by C. So as you all might know, as an ellipsoid is simply nothing but a distorted and rotated possibly sphere. So the matrix A gives you the distortion. So now, as long as the matrix A is what is known as a positive semi-definite matrix. So I'm not so sure if Chandru covered it in linear algebra. So basically, matrices are with positive eigenvalues or positive semi-definite. So this is once again a set of matrices which you will encounter over and over throughout your things. So the interesting thing is, if an ellipsoid is defined by this set, then the volume of the ellipsoid is simply given by pi times the determinant of A inverse. This is kind of interesting, but it's now the problem is clear. Now you can frame it as an optimization problem. Simply that minimize determinant of A inverse subject to each of these points being within that ellipsoid. But unfortunately, directly that problem is actually very difficult to solve. However, there is a variant, which is instead of minimizing the determinant, minimize the log of the determinant. You can see that they are the same. I mean, log is a monotonic transform, they are the same. But while we just had the determinant, it was actually not an easy problem to solve. With the log, it actually becomes a convex optimization problem. The subject, recall the optimization variables are A and B, okay, not the x's. So your objective now becomes minimize the log determinant of A inverse subject to each of the points x1, x2, xm satisfying this constraint. That is, your norm of ax plus b must be less than or equal to 1. So this is a pretty simple optimization problem to frame, but you must again, this looks pretty complicated, but this is actually a very standard convex optimization problem. So what I'm trying to convey here is there are two, you must be careful in framing the optimization problem. If you had just kept it a determinant, you would actually not been able to solve the problem. But the knowledge that the log det actually is a convex function, that actually helps you. I will not tell you what a convex function is, but you should be careful about framing the problem as well. If you frame the problem carefully enough, then what looks like a very complicated problem can actually be very simply solved by generalized solvers. So I will not again give you what the solvers are, but that's about it. Okay, so the take home is finally, forget all the things, the take home I want you guys to take home is simply gradient descent. If you can just take that, I think I'll be happy. So the optimization it's a very useful and very powerful and very pervasive branch of mathematics. It is like very well studied, but still the convex optimization problems, even though they are very well studied, even they don't have very efficient algorithms. They only have reasonably efficient algorithms. And there are many other problems which don't have any algorithms at all. So there are like very, very many number of problems for you to work on in case you want it. If you're interested, you can like talk more. Lunch break is now, I guess. So thank you. So you can have any questions you can ask. Okay. Okay, so that is the definition of, an ellipsoid is defined by this matrix A and this element B. So I will not really go the set of vectors B such that this satisfies this constraint forms an ellipsoid actually.
What is that base 2 to the norm?
So that's 2 norm. That's basically the norm of the vector. Length simply x. If the norm of vector is simply square root of x1 squared plus x2 squared plus x3 squared, right? That is the norm of vector x.
Okay. What is it? What is 2 there then?
So it's the 2 norm. So you are taking squared and square root, right? So actually that's called the 2 norm. You can actually take to the power p and take to the 1 by pth root. It's actually possible. That becomes the pth norm.
And how come log determinant of A inverse becomes a convex function?
That's a pretty complicated question. So you actually take the Hessian and can solve the problem. So determinant by itself is not easy to solve, but log det becomes, because even though they have the same solution, they are not the same problem. So you should be careful about, what you really want is a solution. You don't really care about how you frame the optimization problem to get that solution. There are two distinct, you could have the determinant and the log determinant. They are two distinct problems. They have the same solution, but they are two distinct problems. So you can solve this problem easier than the other problem. So,
thank you.
Yeah. Okay. If you have no questions, you can ask me during the lunch break or something.